Welcome back for Lecture 4. Today we're going to continue our introduction to differential privacy with Part 2. The last time, what did we see? We saw a randomized response and the definition of differential privacy. Today we're going to continue by showing a new algorithm for differential privacy, perhaps one of the most important algorithms in differential privacy, which is the Laplace mechanism. And then we'll conclude by going over some useful properties of differential privacy, including post-processing, composition, and group privacy. I'll comment that presentation in today's lecture is based heavily off of section 3.3 of Dwork-Roth, so I recommend that as a good reference, as well as some of the coverage in the early chapters of Vadhan's survey. Okay, so last time we talked about randomized response. Randomized response was a cool algorithm. It was very simple, very neat, but I'll say it's a little bit limited. At its core, it works in the setting where an individual's private data is either 0 or 1, just a single bit, and it privatizes that bit. It can be generalized to say categorical data, say if you know their number, their sensitive data is the number between 0 and k, or an item which can take one of k different labels. But it's still a little bit, specific to that type of setting at its core. And instead today we're going to talk about a sort of general way of answering numeric queries. That is, if you ask any query about a data set which has a numeric answer, then the Laplace mechanism may be applicable for this type of thing. So before we introduce the algorithm itself, we're going to start by introducing a core concept known as the sensitivity of a function. The sensitivity is a very natural quantity which comes up when doing differentially private data analysis. So what is the sensitivity? Well, first of all, let's suppose we have a function f, and this is going to, as usual, take like an input in some domain, so some domain x. It takes n data points, and the thing is, it's going to map from this data set to the real numbers. So in particular, we're going to focus on a real value data set, and in particular, where the output is k-dimensional. So then we have that the L1 sensitivity of the function f is defined as follows. And we're going to generally use the symbol delta to represent this. It's going to be equal to the max difference over all neighboring data sets. And of the following quantity. The difference between f of x and f of x prime, and then you take the L1 norm. Okay, this is the L1 sensitivity. You essentially take the max over all neighboring data sets, and recall that neighboring data sets are those which differ in exactly one entry, and you compute the function value on these two neighboring data sets, you take their difference, and you take the L1 norm. This is the L1 sensitivity. So we'll use the symbol delta, and when it's clear from context, we might omit the f, just saying that delta is the sensitivity. And in addition, I'll mention that sometimes we'll just call it the sensitivity in the instead of the L1 sensitivity, just because this is the one we commonly use for the Laplace mechanism. Let me note, so let's try to interpret this quantity a little bit. Why is this natural? Why would we want to look at this? Well, remember that differential privacy essentially says that we're trying to mask the contributions due to the addition or removal of one individual. Well, if we want to mask the contribution of a single individual, then we want to understand how much the function itself can change when we add or remove one individual. So this essentially looks at that value. How much can the function change when we add or remove a single individual? Now, one thing here that might not be completely obvious is when we say how much it can change, why do we look at the L1 norm? Why not say the L2 norm or some other measure of how close or far these two functions are? Well, the reason is a little bit technical, in the sense like it's not super hard, but it's basically the notion that will be natural when it comes down to proving that the Laplace mechanism works. In particular, in other settings, for example, if we're doing something known as the Gaussian mechanism, which will use Gaussian noise, then in fact we'll use the L2 sensitivity instead of the L1 sensitivity. But for now, we're just going to focus on the L1 sensitivity for this lecture, and it's a very core concept in differential privacy. I'll comment, though, one last note before we move on, that I said the L1 sensitivity versus the L2 sensitivity. If we're just dealing with univariate functions, that is when k equals 1, then these two things would be equal to each other. It'll literally just be the distance, the difference, the absolute value of the difference between the function on the two data sets. But when k is greater than 1, then these could in general be like up to a square root of k factor off from each other. Yeah, so it's kind of like a square root k difference multiplicatively with L1 versus L2 norm. But that's not going to be too important for us, at least right now. So as a running example, we're going to use for now the function f. This is the same one we used in the last lecture. So we'll use the function which is just the average of a set of bits. So imagine we're just averaging these bits where, you know, xi is in 0 or 1. And the question is, what is the sensitivity of f? Well, it's not too hard to see that if you change, you know, one bit to from a 0 to 1 or 1 to 0, then this will change the sum by at most 1, and therefore will change the overall absolute value of the function by 1 over n. So it's not too hard to see that the sensitivity of this quantity is 1 over n. Okay, so that's the sensitivity. Let's move on to the next key piece that we need before we introduce the Laplace mechanism. And that, of course, as the name suggests, is the Laplace distribution. So the Laplace distribution is the following distribution. Let's write what the PDF looks like. So it has like, we'll focus on the case where the location parameter, it has two parameters in general, but in this class we'll generally be focused on a single parameter version. So we'll use that the location parameter is equal to 0, which means it's sort of centered at 0. But the more important one you should focus on is the scale parameter, which we'll have as a value b. And the Laplace distribution is the distribution with the following density. So p of x, so the PDF, the probability density function at some point x, is equal to 1 over 2b exp of minus absolute value of x divided by b. So that's the PDF of the Laplace distribution. It's very simple. What do I want to say about this? There's a few key facts that we'll need to know. The first thing is if it has scale parameter b, then the variance of it will be equal to 2 times b squared. You can see some visualizations of what this distribution looks like down below here in this figure at the right. This is from Wikipedia. So you can see that, you know, here's a scale parameter b equals 1, and you can see this has the lowest variance, and then a larger scale parameter, it's sort of wider looking, and b equals 4 is even wider looking. We'll sort of disregard the last one because we don't really care about when the mean parameter is non-zero for now. So you can see these are some visualizations of it, and if you've got a keen eye, you'll notice something, and basically looking at the pictures as well as the PDF here, you'll see that this is essentially the exponential distribution. So like the Laplace distribution is sort of like, is exactly equal to like a two-sided exponential distribution. And this can be seen, if you're not convinced, I'll claim that the exponential distribution, it's supported as follows. It's supported on just the positive numbers. So it's like takes x in 0 through infinity. And it has density p of x, which is proportional to x to the minus like c times x, where c is some constant. But the point is, you see that it's essentially the same form as we have here. The difference is that the Laplace has x in the real, so it takes the whole domain, not just the positive numbers. And p of x is proportional to x of minus c times absolute value of x. So it's a pretty small difference. It's just saying that it's like essentially two-sided. Yeah, you just mirror it over the y-axis. As a final comparison, let me also just mention another distribution you might be familiar with, which is the Gaussian. This is kind of similar to the Laplace in the sense that it's, it's defined, it's supported over the entire real line. The difference here is the fact that the PDF is proportional to x of minus c times x squared, where again c is some constant. So like, don't worry about the fact that there's no absolute values. The squaring does that automatically. But what I'm trying to say here is the fact that this has a lighter tail than the exponential distribution. In particular, you can see that as x becomes large, then this PDF dies faster. So yeah, so it has lighter tail than the Laplace distribution, meaning it has somewhat stronger concentration, though both decay at least exponentially. So both tails fall off really, really fast as you get further away from their mean. But the Gaussian would decay somewhat faster. But that's not really too big a deal in the sense, like I said, they're both going to decay very quickly. Okay, so now with the Laplace distribution in hand, and with us comfortable with it, let's define the Laplace mechanism. It's incredibly simple, even simpler. Okay, maybe not simpler than, we had to go through all this work to define it. I'm not going to tell you it's simpler than randomized response, which is perhaps the simplest, but let's just say it's really simple. Yeah, so let's suppose f is basically working in the same setting that we did before. It maps from some domain x to the real numbers in k dimensions. Then the Laplace mechanism is the following algorithm. All you have to do is, I'm going to say it's M. M is the name of the mechanism, or the algorithm in this case. And it takes in some input data set X. And what it'll do is compute f on that data set X. So this is the function that we care about. And then we add on Laplace noise in each coordinate. So remember that this is going to be a k-dimensional value, this function, since it maps from a data set to a vector of length k. So we have to add something to each coordinate, y1 through yk. And what are these yi's? Well, we're just going to say that the yi, they're sampled, say, iid, independent and identically distributed, according to Laplace with parameter delta over epsilon. Sorry, I guess I didn't define this notation I'll be using. Let's say that, Laplace B refers to this distribution right here, the one with scale parameter B and this PDF. So all I'm saying here is that the yi's are sampled iid from a Laplace distribution where the parameter B is equal to the sensitivity divided by epsilon, where epsilon will, as we'll see, is the privacy parameter we want. Roughly, if you think of epsilon as being a constant, then this really says you add noise to each coordinate proportional to the L1 sensitivity. Okay, so that's the Laplace mechanism. Let's see, let's return to our running example. So remember, our running example was f equals the average of a bunch of bits, xi. And we're just going to basically straightforwardly apply the Laplace mechanism. What are the parameters? Well, what do we know here? So f is just this quantity here. As we said before, delta equals 1 over n. And, we have k equals 1. Therefore, we're going to have the estimator that p tilde is equal to f on x plus a random variable Laplace, which is of magnitude 1 over n times epsilon. So that's what our estimator is going to be, or what our privatized value is going to be. We haven't argued that it's going to be private yet. We'll do that in the next section, but let's just see how accurate it will be for now. So we'll analyze this very similar to how we did before. So recall like another way we said like the parameter, we're going to say that P is equal to F on X, basically the true average, and P tilde is our estimate of how good it is, which is also private, as we'll see. So we'll analyze this very similarly to how we did before. So what's the expectation of P tilde? Well, just by linearity of expectations, we can see that this is equal to expectation of, I guess there's no randomness in this part even, so we don't have to worry about this. This will be equal to f of x, which is just P, plus the expectation of this Laplace random variable. But the thing is, we said that this Laplace random variable will have expectation 0. So this is equal to P. So in other words, we can see that this estimator, the statistic we defined, is an unbiased estimate of this P. Okay, so that's the expectation. Now, similarly, we can compute what the variance is. The variance of P tilde is equal to, so this doesn't change, so that wouldn't show up in the variance calculation. It's just going to be equal to the variance of, Laplace 1 over n epsilon. And this is equal to, just using the formula we had before, this is equal to 2 over n squared epsilon squared. Good. So now that we have both the expectation and the variance, now once again, I'm going to do this the silly way. There's like better ways, which I'll allude to. But for example, one way of doing this is by Chebyshev's inequality, which, as we mentioned last time, will allow us to bound the difference between P and P tilde by, essentially the standard deviation up to a constant, with sort of constant probability. So this is going to be over 1 over n epsilon with reasonable probability. Now, this is, like I said, this is a silly analysis of this because, like I said, the Laplace random variables have rapidly decaying tails. So really, yeah, let's do the better analysis. In fact, what we can really say is that, P minus P tilde, this difference is going to be less than or equal to, what do I want to say? I have this fact that we'll use. Let me introduce a fact about Laplace random variables. So we have that if y is distributed according to Laplace with parameter b, then we have that probability that y is greater than t times b is less than or actually is exactly equal to x of minus t. So this is an exact relation, and this just follows by looking at the Laplace distribution's tail. That's all you have to do. Okay, so with this in hand, then what are we going to do? We're going to just say that what we can do is set sort of a sort of corollary of this fact is the fact that probability that y is greater than or equal to b times log, say, 1 over beta, this is going to be equal to beta. So essentially, what am I trying to say? The probability that it's large is pretty small. So let's just substitute that in here, because essentially this difference is going to be distributed exactly as Laplace 1 over n epsilon. So this is going to be less than or equal to say parameter b, so this is going to be just log 1 over beta over n times epsilon with probability 1 minus beta. So this is a much stronger bound than what we had here. Okay, so yeah, that's how we analyze the accuracy of this sort of the Laplace mechanism on this example where we just wanted to average these bits. And let me compare this with what we had before. So let me just highlight, the error is bounded by roughly, like I'm just being approximate here, 1 over n epsilon. Now compare this with the error of randomized response from last lecture. That had error less than or equal to O of 1 over square root of n times epsilon. In other words, you can see that in this setting, the error decays quadratically faster when we focus on the dependence on n. And so this is sort of much better in terms of the accuracy compared to randomized response. Okay, now that's showing that it's going to be significantly more accurate than randomized response, but we haven't actually argued that this is at all private. So let's proceed and prove that the Laplace mechanism is epsilon differentially private. So let me just write that here. Laplace mechanism is epsilon dp. So let's prove this. And how do we do that? It'll go as follows. So what we're going to do is let x and y be neighboring databases. And so the function, the mechanism, the Laplace mechanism run on these two will be mx and my. These are the random variables because these are going to be, a random, have random values. And so like we're going to use values, or we're going to use, what do I want to say? The x of z and the y of z. These are going to represent the PDF of the Laplace mechanism on x and y respectively. So that is kind of, it tells you the PDF that m of x applies, has at point z, where z is some point. Okay, so we're going to show essentially from first principles that this is differentially private. I mean, first principles, I'm going to say that, for all x, y, which are neighboring, as well as, and for all z, then the ratio of the px and py is bounded. That's sort of going to be the plan. We're going to take an arbitrary setting of x, y, and z, and then we'll show that the ratio of their probability densities is bounded. So let's just do exactly that. So px of z divided by py of z. Recall that differential privacy says that this is bounded above by e to the epsilon. So okay, let's just write this out. And we can write it out as a product, like y is a product. So we're going to write this down once for each query that we're doing, once for each dimension of the output. And we're just going to write this as, exactly what the PDF says it would be. So let me write this here, and then we'll explain it. Okay, so what we've got here is we basically just wrote out the probability density function. So note that this can be decomposed into its coordinates because all of them are independent of each other in terms of the random variables. We're adding IID noise to each coordinate. So, and then what is the probability that, this will take whatever value zi in coordinate I? Well, this is just by following the PDF of the Laplace distribution, which we saw is proportional to x to the, e to the value of x over b. Well, remember that b is going to be delta over epsilon. So this goes in the denominator, and the numerator will have the distance from the true value, which is f of x on I. Note that there's a normalization term, but since it's in the numerator and the denominator, they both cancel out with each other. So this is just the ratio that we're looking at. And you can see the denominator is going to be the exact same thing, except with y instead of x. Okay, so that's the starting point. Now what we're going to do is we're going to sort of group these terms in the following way. So we can write this as a big product over I equals 1 to k, and we'll just sort of group these terms together. In the sense, coordinate I will be grouped together, so this becomes negative epsilon over delta times, it'll be essentially this minus this because you're moving it to the numerator. So it'll be f y sub I minus z sub I, absolute value rather, and then minus f x sub I minus z sub I. Yeah, so this is just grouping the terms together. And what we're going to do now is use the triangle inequality, which says that essentially we can use the fact that they're both kind of, we're using their differences with respect to zi, so we can also look at their differences with respect to each other. So again, this is by triangle inequality, and this can be replaced by the following. Difference between f of y sub I minus f of x sub I. Now, we're pretty much done at this point in the sense that all we have to do is some rearrangement of terms. So since it's a product of exps, well, we can always bring the product inside the exponent. So this becomes minus epsilon over delta summation of f x sub I minus y sub I. And the nice thing is that this is looking at the absolute value of each coordinate and taking the sum over coordinates. Well, we know this as exactly equal to the L1 norm. That's the definition of the L1 norm, in fact. Yeah, the L1 norm. Now, the last step of the proof is simply to note the fact that we said that delta is equal to an upper bound on the L1 norm. So all we need to do is the following. Sorry, I seem to have tracked an extra minus sign somewhere. Yeah, we don't want, the minus sign should have disappeared. I think right about here. This shouldn't be here because we move this up to the numerator, so it becomes positive. Similarly, it disappears here, here, and here. Okay, but now all we have to do for this last step is basically use the fact that delta is greater than or equal to the L1 sensitivity, and this becomes exp of epsilon. And that's the end of the proof, because that's exactly what we were trying to show, that the ratio of the PDFs at this point z is upper bounded by exp to the e to the epsilon. And that's exactly what we're trying to do. This holds for any neighboring data sets as well as any point z, so it holds in general. So that's the proof. It's pretty simple, and it perhaps isn't so surprising in the end. Why not? Because just take a look at the PDF, which shows that the PDF decays exponentially, and the definition of differential privacy kind of has this exponential in the definition as well. So in retrospect, it's really kind of seemed to be the right distribution to characterize differential privacy. Okay, so let's see, now that we have the Laplace mechanism in hand, and we've seen that it's provable, we've proved something about it, let's see a few different applications of it. By that I mean, like, what are simple classes or types of queries that we might be wanting to ask about, that we might want to solve privately. So one of them is counting queries, which is essentially what we've already seen. Like, let me just write something. Like, it's a counting query is asking how many people in X satisfy property P, where X is our data set and property P is whatever property we want. So for example, this is very similar to the average query that we were doing before, where property P would be kind of how many of them have bit equal to 1, and we looked at a normalized version there. But here, we're really just going to look at the number rather than the average. Sometimes these are used interchangeably to refer to counting queries as an average versus not averaged. But essentially, what this will do is, if we just ask one question like this, then our function f would be the following. F on x would be equal to summation of xi, where, once again, xi is equal to 1 if p on sort of x on, if p is true for I, and 0 else. So again, this is pretty similar to what we've looked at already, but it just sort of counts how many people satisfy property P. It's very easy to analyze this. Again, the delta is equal to 1, just by changing one thing from 0 to 1 or 1 to 0, can only change it by at most 1. And from there, the Laplace mechanism would be m on x is equal to summation of xi plus Laplace of 1 over epsilon. Just because, delta is equal to 1, so that's all the magnitude is. So if you just want to answer one question, you can add noise, which is just proportional to 1 over epsilon, and in particular, this is independent of the size of the data set. So for example, if it's a huge data set and you want to count the number of people who satisfy something, and you just, add constant magnitude noise, because if you consider epsilon to be a constant, then this is going to be fairly small in comparison to the size of your data set, or in comparison to the size of the query you're asking. And therefore, it won't really hurt your accuracy too much. Okay, so that's just one query, but let's suppose we want to ask many queries instead of just one. So in particular, suppose we had k counting queries. So k counting queries of the same form. And now our function is going to be going to be a vector, say like f1 comma f2 all the way up to fk. So we have a bunch of counting queries which are all specified in advance. So this might ask, how many people have blonde hair. This one might ask how many people have income at least like 50,000 a year, etc. So these are our k counting queries. And the Laplace mechanism is just going to be the same thing as we had before, where, mx equals f on x, which is now going to be a vector, plus, a vector of y's. But the question is now, we have to specify what exactly the parameter here is going to be. So y is going to be like a vector of, k Laplace random variables. But what is the parameter here going to be? And like we said, we know it should be equal to delta over epsilon. But what is delta? Well, like we said, delta is going to be the maximum L1 sensitivity of this vector. So how big is the maximum L1 sensitivity of this vector going to be? I claim it can actually be quite a bit larger than before. Before it was just 1, but now it can go from being, it can have quite a large sensitivity this time, and I'll claim that the sensitivity in L1 distance can be as large as k. And why is that? Well, let's suppose there's just a single individual who we'll call individual, say x. Well, x maybe has everything false about them. So say f1 on x equals 0, f2 on x equals 0, and all the way to f of k on x is equal to 0. And let's suppose they changed their data from x to y, where y is 1 on each of these. So f of 1 on y is equal to 1, and so on all the way up to f of k on y is equal to 1. So what I'm saying is that one individual could have properties that lead them to have everything be 0, and then switching them to another data point can lead them to having everything plus being equal to 1, kind of, because you're using the same data set to answer all of these queries. So therefore, it can differ by 1 in each coordinate, and the overall sensitivity would be proportional to the number of coordinates. And that's where we get the overall L1 sensitivity equal to k. This is essentially just the L1 norm of f on this individual x minus f on individual y. Okay, so that justifies the fact that the noise is of magnitude, the delta is of magnitude k. So therefore, you would add Laplace. We can answer this now. Now we know that this is going to be Laplace k over epsilon. So therefore, the magnitude of each counting query is going to be of magnitude k over epsilon. So there's two things that we're going to note here before we proceed, just a little bit of discussion. Point one is that, the way we were doing this is that we specified all the queries in advance. In particular, like we sort of specified f1 through fk all up ahead before doing anything with the data set, and we answered them all at once using privatization using the Laplace mechanism all simultaneously. In other words, what we might say here is that this is a non-adaptive way of answering the questions. Like, we didn't get to see the privatized result of query 1 before we chose what query 2 is, and so on. They were all specified ahead of time. And you might wonder, is this necessary? Can we do this adaptively? Well, the answer is yes. We can make this strategy adaptive. What do I mean by that? In the sense that it'll be possible to answer k queries adaptively without paying any sort of cost in how much we have to pay. So we'll see that a little bit later when we get to composition. And two, let's comment a bit on how good this defense is. Like, how private is this? Let's think back to 2 lectures ago where we talked about de Noor-Nassim. And recall that in that time, we showed that if there's omega of n queries, and there is O of square root n noise, then there's an attack. That means, we remember this means it's blatantly non-private, and it means that, there's no way that the curator could answer this many questions with this little noise. However, what this result says is essentially if there's O of n queries with like theta of n over epsilon noise, this is just substituting in k is equal to n here. So if there's O of n queries and theta of epsilon over n noise, then this is private. So you can see that if you add this much noise, let's just fix ourselves to looking at things with n queries. We can see that if you add n noise, then it's safe. If you only add as little as square root n noise, then there's an attack. So here's a very big gap for some reason. You can see that if you want it to be private, you have to add much more noise than where we have an attack. So the question is, like, can we, there's sort of one of two cases here, or it could be a third case entirely, but like sort of the two obvious cases are one that, what if the only way to prevent sorry, let me say this a different way. What if there exists some different attack, different from the de Nord-Nisim attack, which works all the way up to order n noise, and therefore this result is tight? Or the other thing would be, what if it's possible to add even less noise to each query and still remain it being private, therefore showing that this attack is tight? And the kind of cool thing is that the latter is true, in the sense that there's a better way of analyzing differentially private things, and we'll see this somewhat later. It's possible to get by with O of square root n over epsilon noise, and it still be private. But this uses something called advanced composition, which we'll get to in the next lecture. But it's kind of cool to see the interaction between this and the de Nord-Nisim attack. It goes, I think I mentioned this before, from being blatantly non-private to private when you do it analyze the right way. Okay, and so the last thing we're going to do is talk about the Laplace mechanism. The last application of the Laplace mechanism, at least, is going to be talking about histograms. So now histograms are a kind of different type of query. Why are they different? Well, with counting queries, recall that we had to be very pessimistic. We said that when we were doing a query, when we're doing a set of queries, we said that changing a single individual could result in in all of them changing at once. The answer to every query changing at the same time. But suppose we were working in a sort of more restricted setting. What if we know that that an individual can only have a single one of these be 1? For example, say like x to y. Now it would be something like a setting where f of 1 of x equals 1, and f of 2 of x is equal to 0, and so on. Everything else is equal to 0. Whereas f of 1 on y, say equal to 0, but say everything else except for one thing is equal to 1. So the idea is that suppose we're in a setting which we'll call a histogram setting for reasons which may become apparent. An individual can only satisfy one of these things. They can fall in one of these different bins, so to speak. You can think of them as sort of different bins. So what do I want to say? This essentially asks how many people fall into a specific bin. For example, this could be someone's age, for example. So a type of histogram query would be asking how many people are X years old, and let's pretend that these are like whole numbers. And you answer this for all X simultaneously. So specifically, then this would have like f. The function that we're going to look at is going to be, a vector similar to before, f of 0 on the data set x, all the way up to f of k minus 1 on x, where the sort of ith query here is going to be asking, f sub I on individual x is going to be, asking, is x I years old? And like I said, this satisfies this property because an individual can only be one age. They can't be both 1 and 2, and so on. You can ask this for anything where sort of an individual falls into one thing, exactly one bin. For example, you could ask, favorite ice cream flavor or eye color, something like that. But okay, so we'll see that in this case, we can actually do a much better sensitivity analysis and get much less error than we did before. So this is what the query looks like. And what is the sensitivity in this case? Well, in this case, we basically argued it over here in the sense that changing one individual's information will have a sensitivity of, I guess depending on how you count, either 1 or 2. Let's say it's equal to 2. Because I'm saying we're going to use the swap one person's value. So you can see that essentially it'll decrease one count by 1 and increase another count by 1. So if we kind of want to write this out as a as sort of like, explicitly as a sensitivity calculation, be something like this. So I'm just looking at this on, sorry, let me write this as with these being sort of whole data sets here. So what we can say is that for a single coordinate, this would be equal to sum over the coordinates of the distant differences. So there would be a single coordinate. Let me just say it like this first. F x I minus I on y. And this is decomposable into a bunch of different things. One of them will be sort of when one thing was 1 before and 0 after, plus a bunch of zeros, plus one where this is going to be 0 and the other one is 1. Note that actually these will have values for all the other individuals, but I've sort of factored them out of because it'll be the same, so they'll cancel out. For all the individuals we left untouched. So the point is, overall, this will give us an overall sensitivity of 2. Okay, so with this in mind, now let's look at what the Laplace mechanism will give us. So we have fx plus, y1 to yk, where, like I said, this is just going to be a k-dimensional vector, so you have to add noise to each coordinate, where yi is going to be distributed as Laplace of 2 over epsilon. So this is quite small. In particular, this is totally independent of the size of the database, but it's also independent of the number of queries that we're performing. Remember, before we had to add noise proportional to the number of queries we were asking, but due to the nice structure of the queries we're asking here, we only have to add it of magnitude 2 over epsilon. Okay, so let's see how much error we actually incur here. So this tells us, this algorithm is going to be private. We know that from properties of the Laplace mechanism. But how much error did we incur here? So we can analyze this in kind of 2 ways. One is just by using the same type of counting query error that we did before. Basically the same thing here. So one thing we can say easily is that, fi on x minus, I guess let me write this as m of x, which is the mechanism's output. This will be sort of less than or equal to, say, 2 over epsilon log 1 over beta with probability 1 minus beta. Okay, so now that's nice, but let me show you something even stronger. What if we want to bound the error in all of these simultaneously. So let me show you the following. We can actually write a slightly different tail bound. So this is just using the fact that we showed before. Let me bring that up again. So this was our little, let me copy this and bring it down. Distance. But okay, so this is our tail bound that we have, and this is what we applied right here. We just said that the error that we incur here is going to be, 2 over epsilon times log 1 over beta with probability 1 minus beta. But instead, we could in fact use this same tail inequality and say that essentially the same quantity. In fact, let me just say this is less than or equal to 2 over epsilon log k over beta with probability 1 minus beta over k. And I didn't do anything fancy here. I just subbed in a different parameter into this bound. And that's all that happened. Now, what I'm going to do is use a union bound over all i's. And from here, we can say that for all I simultaneously, we have the following bound, that f I of x minus mx of I is going to be less than or equal to 2 log k over beta over epsilon. And let's see how powerful this is. This is pretty strong because of the fact that we can ask k queries, but the only cost that we pay is going to be logarithmic in the number of queries we ask. So this says that we can really do histograms over very, very large domains, and the cost is really minimal. So this is very useful and surprisingly accurate. This is perhaps one of the more practical and useful algorithms in differential privacy, basically differentially private histograms. So that's it. We've seen a lot of different applications of the Laplace mechanism as well as its definition and introduction. So this is one of the core tools in differential privacy. Next, we're going to continue on and talk about various properties of differential privacy, which will be instrumental in our future investigation of differentially private algorithms.